Okay, looks like we can get started. Welcome back, everyone. We're now into week 3, starting off section 2.3 on continuity. Other elements of announcements are we launched our very first quiz on week number 2, and we'll be posting the second quiz down here before we make it to our Thursday's class. But welcome back, everyone. Probably the bigger announcement I want to spend some time discussing about is the upcoming exam 1, which is going to be next week on Tuesday. But any questions to start us out so far today? Okay, well, as far as exam 1 goes, it takes a bit of organization to really get this going since there's 2 different modes for this class running, all put into one hybrid class. So the exam will be held on Tuesday, February 3rd. That'll be the official day. And if you're in the in-person section, meeting in Idaho Falls, room 215, the expectation is we'll be taking the exam together on class time a week away from today, starting at 4:30. If you're in the online section, which is the majority of the class, then there's different modes that you might, or different testing centers that folks might be participating in. And I send direct instructions to everyone in the class through the Canvas inbox system here on those instructions. Good evening, Haley. And one thing I did notice, however, is Monday was the last day to add drop classes, and we did have 2 additional students add our class. So I think I have instructions sent to one person, but one person's still missing. So if you're that one person and you haven't gotten instructions for scheduling the exam, I'll get that sent out soon. Probably first thing I'll do on Tuesday's class or before Tuesday. Yeah, absolutely, Haley. So as far as the instructions go, through the inbox system, I sent instructions, say, if you're in the Pocatello Testing Center, I gave instructions how to schedule the exam for that testing center. And same if you're in the Pocatello, closer to the Pocatello Testing Center. Some people are far more remote, say Meridian, Twin Falls, etc. And I sent instructions as well. And essentially, this is about what it looks like. Let me give you just a quick view. It's similar for Idaho Falls Testing Center as well as the Pocatello Testing Center. But let me go to isu.edu just to give you a view for what this looks like. And let me see here. I want to go testing center. That was misspelled, but should work. And then let's see. I forget exactly where my link is. Give me a moment. Oh, I'm in Idaho Falls. That would explain it. And finally, I should have loaded this up before class started, but almost there. Okay, this is about what it looks like. For the Idaho Falls Testing Center and the Pocatello Testing Center, I sent you a link that looks like this for the right particular campus. Our exam is on Tuesday, February 3rd. So what you would do when you see this link is click over to the February, and I let this exam be open for a range of days. The reason for that is the testing center has to work with your schedule, and it's conceivable that if everyone in the class schedules for 4:30, the Pocatello Testing Center could run out of capacity. So I leave it open for a range of times you could select on Tuesday. You could select anything that works best for your schedule. So if you click on, say, 4:30 p.m., oh, hang on, click next on how long the exam is, 75 minutes, and then you'll fill out the information to complete the booking of that exam. And that's a great question as well. Thanks for asking about that. If you can't make it on Tuesday, you don't have to send me an email. I've set up the exams I'm scheduling for these testing centers, no matter which one you're at, to be open for a range of days. Again, the testing center could be overloaded. These times might get a little bit restrictive. So if there's a better day, you can take the exam between Monday through Thursday. So these are the times that's open for the Pocatello Testing Center and the Idaho Falls Testing Center as well. And then that's kind of weird if you think about it. This is a hybrid class where there's an in-person section. I'll be here at Tuesday 4:30, specifically on one hard date and time. And so just for the sake of addressing the fairness issue, if you're on the in-person section coming into the classroom today, I let the exam be open for scheduling on the same dates as well. So if the class time just works for you, I'll be here 4:30 p.m. on Tuesday, February 3rd. But everyone in the class has arranged from Monday to Tuesday through Thursday rather. So even if you're in the Idaho Falls the in-person section, if a different time and date works better for you, let me know at any point, and I can send the exam to the Idaho Falls Testing Center for the in-person people as well. That way it doesn't feel like there's differential treatment where the in-person people have to make it on a precise date, but then the online section has all this flexibility. That just seems like kind of a weird fairness issue altogether. Lauren said, I tried to make an appointment for the 2nd on the Pocatello Testing Center, and it was denied and said it was open on the 3rd. Oh, that's strange. I'm going to give them a call. It should have been open from these particular dates through on the Pocatello Testing Center. So I'm going to give them a call on the first thing Wednesday morning to see what's going on with that. Okay, thanks for letting me know about that again, Lauren. Anyone else have that same kind of issue with scheduling the exam? Where maybe you try to schedule it on the 2nd or the 5th and that you got something like it's denied? Okay. Yeah, again, I'm going to take a look into that and I'll follow up with you directly, Lauren, to see what's going on there. But aside from that, once again, the instructions have been mailed directly through Canvas on how to schedule your exam one. They'll be open on a range of days between the 2nd and the 5th. That's the intention. I'm going to follow up on what I might have messed up. That could have been a problem on my end when I set up that exam for this class. And if you don't see those instructions, double check your ISU email address as well, since if I send a message through Canvas, it also bounces to that ISU email address. And if you can't find those instructions, just send me a direct email at any time, and I'll send you that information right away. So again, it's kind of tricky running a class like this where there's different modes of taking exams and so on. Any questions at the moment, folks, about scheduling the exam? Okay. Other things I want to mention about the exam is it's going to be this coverage here, sections 2.1, 2.2, and 2.3. And I'm a big fan of parallelism when it comes to writing out exams. Pretty much my process is I found out what I wanted to assign the problems in when I created the WebAssign problem. Then I wrote my lecture notes based off the WebAssign problems themselves. And then the quizzes are based off the problems we did in class, WebAssign problems as well. And finally, when I went to write exam one, I just looked at what I assigned, what we did in class, what came out as a quiz, and I based exam one on that material. We did a lot of graphing problems, so you can expect to see those same kind of graphing problems as well in the exam. We did some limits with algebraic methods, so you should see corresponding similar problems as well in exam one. And so that means there's a definite kind of order of operations when it comes to preparing for the first exam. Very first thing I would do is get caught up on the quizzes. There'll be a quiz one, a quiz two that's going to be posted. Quiz two will be due on Thursday, but if you decide to turn it in early, I'll grade that one early and send you back the feedback so that you get that extra practice on quizzes or extra feedback as well. After that, go into the WebAssign homework and get caught up on those particular sections, 2.1, 2.2, and 2.3. Once you're fully caught up on the homework, you're practicing problems just as they would appear on a real exam. A great way to do those problems is just copy them down on a notebook, write out the step-by-step solution if it's a multi-step problem like you would on a real exam, or you would on, say, a quiz problem, and you're getting a good feel for what the exam questions are going to look like and how to solve them. After you get caught up on the quizzes, the WebAssign homework, then it's a good idea to start looking into additional problems just for further practice as needed. I have two versions of practice exams. Probably one document you want to have pulled up and just ready to look at, maybe on a separate screen, maybe printed out, would be this one. Definitely don't bring it to the exam in a testing center. They won't accept it. It's going to be the last actual page on the real exam one, so it's already provided. And it looks like this. This is the direct information you're going to see on the very last page of exam one. I felt like for the material we covered, the limit laws was a definite good idea, and a statement of continuity, which functions are continuous as well. So if you have this pulled up when you're studying for the exam, then you'll know exactly what's provided, where to find the information as needed, and also will inform you on the content that's not provided, the things that we have to have memorized for the purpose of the exam as well. After that, here's the two versions of the practice exams. Version 1 is problems just out of the textbook, primarily odd problems. So you can click and see the answer for immediate feedback. Some problems I think I assigned were even just because they were really good problems. So if you have questions on the solutions on any of those, don't hesitate to reach out. Haley says, will there be an even amount of questions for each topic, or will there be more questions on one of the topics? I would say it's going to be about proportional to what we did in class. So we've spent a good amount of time, for example, on graphing. So you should expect a proportionate amount of problems on those graphing sets. As far as it goes from a section by section basis, I would say it's going to be pretty even for the emphasis on section 2.1, 2.2, and 2.3. There won't be, like, say, a whole lot of questions on 2.3 and hardly any on 2.1. It'll be even in that sense. And for the amount of questions roughly on the exam, well, that's a good question. I wrote the exam, but I forgot exactly how many. I think it's about 6 questions, plus or minus a question, just for the margin of error there. My goal is to not write a really long exam. There's a 75-minute block for taking the exam, but the way I write the exams is to really kind of go for a 60-minute exam altogether. So you have plenty of time to double check your work, circle back on problems you might have decided to let your subconscious work on, and that kind of stuff. So they'll never be very long exams. That's also to help out the testing center staff. The Pocatello Testing Center, for example, can get overwhelmed if I wrote an exam that's like 20 questions long and 20 pages thick. That would be just an excessive amount of work on their end. They have to print them, scan them, and email them directly back to me. Naomi asks, so the whole exam is 6 questions, or there'll be roughly 6 questions on each topic? The whole exam will be roughly 6 questions. Some questions will have multiple parts. For example, if you look into 2.2, once it loads, this is one whole question with multiple parts. So that would be considered one question together. And the exam is going to be about 6 questions long in total. Other questions at the moment? These are very good questions, by the way, just directly the kind of questions you would want to ask before seeing how the first exam goes. Okay, and again, these are great questions. Not knowing what an exam is going to look like, especially when you're doing so much work in WebAssign, and quiz 1 is really your first handwritten assignment that you're going to be sending out. The idea, though, for as far as exams go, this entire block that you see right here is just going to be duplicated for exam 2, exam 3, and then another one for the final exam. So once we get a feel for what the exams really look like, you'll see just about how each one of them will be down the line. So other things to mention on the exam is definitely don't forget your calculator. Testing centers aren't necessarily going to be able to provide you one if you forgot one. And this exam can be taken without a calculator, but it's just a convenience to have one. In case you're factoring and just want to run some numbers really quick, do some kind of quick verifications, that's nice to have. That's also a good habit because exam 2, exam 3 will use a calculator more and more as we go. So just being in the habit of always having the same calculator with you when you're doing the homework or the quiz and as you go to take the exam will be just a best practice for all these exams that we'll get through. Haley says, I know the Pocatello Center has some, but I'm not sure how many, so they might run out. Yeah, absolutely. And sometimes they might not have the calculator that you want. For example, they do have some basic scientific calculators, But if they run out, they have some like really, really ultra basic calculators that just has plus, divide, add, subtract, no exponents, no square roots. So that could start to get really kind of rough if you're using a foreign calculator with a very, very pared down feature set. So again, getting into the practice of just using the same calculator for each one of your homework assignments and exams will make it an easy transition in an exam setting. Other questions at the moment? Okay, so the rundown is you have the formula sheet. You can reference this to know what's on the exam. This version 1 of exam problems is problems directly out of the textbook. So you can open inside WebAssign the electronic textbook, go to each one of these sections, the exercise set at the end. And these are the problems I felt like best match what we did in class, what you did in the homework, and they would make excellent additions to a real exam. So this would be a long exam. So this gives you just a lot of different variety on what could be asked. For other problems, what I did is I took all the lecture notes for sections 2.1, 2.2, and 2.3 that we're about to get into, and I just converted them into essentially a worksheet. So if you go through these, you've seen this problem before, you've solved it before, but if you want extra practice to run through it once again, that's what this is all about. You can scroll through here, practice these problems again. The solutions are directly on the Canvas webpage on the corresponding sections that we've been completing. So this is my way of saying what we've been doing in class also constitutes a great sample exam set as well. Again, the real exam can't be this long. This is a pretty long exam altogether. But both versions will give you the kind of topics that we'll be looking into on the real exam. Well, that was the major things we wanted to discuss to start out today. Any other questions or comments at the moment? Okay, well, we're going into section 2.3 on continuity. That'll be the last topic on the first exam. And this one is, even though it has a strange new word, continuity, really not too bad after we've gone through, in my opinion, the slightly harder sections, 2.1 and 2.2, just thinking about limits the very first time. That's kind of the rough patch in any calculus class, delving into limits. But continuity is really just more limits. So that's the good news about continuity. Continuity of a function at a number x equals a is defined in terms of a limit itself. And when you look at that equation really, really carefully, you might have a sense of deja vu that I've seen this before. You would be right. We've used continuity quite a bit already in sections 2.1 and 2.2. Let's take a look into 2.2 when we were thinking about limits using algebraic methods. We had something called a direct substitution property. We were told if we're dealing with a polynomial function or a rational function, and the number is in the domain of that rational function, then the limit as x tends towards a of f of x is f of a. And that's the same story here. We're just giving a new word to this direct substitution property. We're calling this a property of continuity. So just to connect the dots, let's match up that color coding. And let me make sure I remember. Okay, so here's the function. So that's the whole punchline to continuity. Essentially, you could look at this direct substitution property again and rephrase it by saying a polynomial is continuous on its domain. So if you take the limit of a polynomial function, this is always just plugging in the number. That's kind of nice in a way. And a rational function is continuous on its domain. So as long as you're plugging in a domain value, you're not dividing by 0, for instance, you're just using direct substitution all over again. But continuity doesn't always work out. That's why we had to work actually pretty hard in some of the problems in section 2.2, doing different things algebraically with the function until we got a simpler function where direct substitution worked, where continuity was actually the fact for the function. And the last part of the definition is, if a function is not continuous at a number a, we say it's discontinuous. or not continuous is fine, but I guess this is a bit of a shorthand, discontinuous. Very first thing we want to do is really look into this definition a little bit harder and compare it against a graph. But any questions at all, folks, with just the initial definition so far? Okay, let's draw just a random graph that's going to go along with this. I want to put a point where there's a discontinuity. Then the rest of the graph is going to be continuous at every other number. Let's put the discontinuity somewhere on the left. Let's go 1, 2, 3, 4, -5 units to the left. So just a random function that we're constructing for our imagination. And let's go 3 units high. And here, we'll put an open circle. So now we know something's going on right at that point. Let's go 4, 5 units high and define the function here. Solid dot gives a function value defined at that height. And now going to the right, let's go 1, 2 units. Let's put just a slight dot right here. Not as heavy of a dot really, although it wouldn't matter, but just a little point right here at height 2. So here's what the function is going to look like. It's a nice smooth curve until we get to here. We hit a hole in the graph, and we've seen plenty of functions with holes so far, just like that. Then it moves on through in this kind of way. It connects through that dot, which isn't massively emphasized, but it's part of the function. And arrowheads aren't required, but it's just my way of conveying it. Continues in that direction forever, continues going down and left in that direction forever as well. And this is our function. Well, there's another way to think about continuity. Sure, we can say it's a property of direct substitution. It occurred to me it's probably a good idea to write that on the notes just to connect that dot. That's all this is, directly substituting a into f of x. But if you're thinking in terms of graphs, the picture you have in the back of your mind for continuity is your curve is continuous. If you can draw it without ever having to lift up your pencil or pen, and right here, you would have to put a hole here, jump up to find a point here, and then continue on. There's no further problems beyond -5, so the function's continuous elsewhere. So what goes wrong at -5? Direct substitution fails really, really badly. So let's investigate this further. If we are looking at the value -5 and we take f at -5, that value is going to come out as +5 altogether. Due to that solid dot, we evaluate and get this number. So that's the right-hand side of this limiting statement. So when it comes to functions, if we evaluate it at -5, it's all about where the output is. It's at a height 5. But the left-hand side is different. The limit is not about where the function is at 5. It's about where the function is going as you get closer and closer to -5. So now take the limit as x goes to -5 of f of x. Anyone happen to see what the value should be for that limit there? Yeah, absolutely. The limit would come out as 3. Again, it's not about where the function is, it's where it's going. And as you're getting closer and closer to -5, coming in from the left, the height is getting closer and closer to 3. The limit exists because as we come in from the right in the opposite direction, it's getting closer and closer to the same height, higher and higher as we get closer and closer to 3. So then that tells us the limiting value on this one is 3 altogether. And we have a disconnect, or better said, this is what a discontinuity looks like, purely looking at it through the analytical side, connecting it to the graph above. So continuity means that limit exists. And so below we can say since the limit as x tends towards -5, let me just get that highlighted there to connect the dots, of f of x is not the same as f of -5. F is, let's use our fancy word, discontinuous. At x equals -5. So that's what a discontinuity would looks like on paper as a graph. But this is the thing that made it discontinuous altogether. The limit just didn't come out the same. So we have discontinuity at that value. If it came on out directly equal, we would have said it's continuous instead. And by the way, this discontinuity has a name. This one is called a removable discontinuity. And the thought about why it's called a removable discontinuity is if you made a slight correction on that, if I can target that point, looks like I can't, but if you make a correction on this graph by redefining the function, putting the solid dot there instead where the arrow is pointing, there's no more discontinuity. You've removed the discontinuity. And so in that certain sense, we classify this category where there's just a hole at one point, one singular point moved around or just gone. That one's called removable. Well, that's, again, lots to tie together visually and through the limit equation down below as well. We'll see it from the other side. What does it look like when it's continuous? Looking into this point here. But any questions or comments so far? Okay, so now the next side, we're continuous here for certain, but let's convey it through the statement because this is the major thing we're really trying to absorb and learn, that limit definition of continuity. So if we take the limit as x tends towards, the x value in question is going to be 2 for this new value or this new limit of the function f of x. Well, this time we're getting closer and closer to 2 when we come in from the left. When we come in from the right, we're also getting closer and closer to 2. So the function values are headed towards 2. Yet at the same exact time, f at 2, f at 2 itself is equal to 2 as well. So there's a nice matchup between the function value outputting 2 and the limit value outputting 2. We could tie this together and say, since the limit as x tends towards 2 of f of x is 2, f, let me write out this way, is equal to f at 2 That's a lot of color coding. Let me put that back. We can now say, this tells us f is continuous at x is 2. And it's also continuous at x is 3. It's continuous at 3.1, 3.01. Every number here would be continuous until we get to that one discontinuity at -5. The value of the limit will be the output of the function everywhere else. Well, that's what continuity looks like, and a discontinuity as well, through analyzing the limit. Any questions or comments so far? Okay, the author has a lot of additional things to say about all this, so here are the further remarks. There's a lot going on with this limit when continuity happens, and this limit when we have a discontinuity. The first thing that has to happen is the function has to be defined at the very first place for continuity to work out. So if we have an undefined, then automatically there's a discontinuity. So if there's an open circle right there, and nothing else, if it's just purely open at that spot, we would have been discontinuous at 2. That's because you couldn't put an f of 2 here. It would have just been undefined altogether. The second thing is the limit has to exist for continuity to work, but that's again because continuity is based on this entire limit statement as well. If we have a does not exist for the limit on the whole left-hand side, does not exist can never equal a function value on the right, and that will give us another automatic discontinuity. So the limit has to exist in the first place, and this is just a major restatement of this value right here. The limit has to exist and must be exactly equal to f at the a value 2 in this example. Well, again, there's lots going on with continuity. I would say that this is not too bad to absorb with what we see here so far on the notes, but it does get a little bit trickier when we look into single-sided continuity. To me, that's the really tricky end about this. So let's turn the page over to continuity strictly from one direction versus the other. Now our limits are a little bit different. We have a limit as x tends towards a from the right. Let me zoom in on that so we can really see these. And all the extra symbols are tied into this one. There's my button. Let's blow this one up as well. So if continuity fails, sometimes you have just single-sided continuity. We have a notion of having continuity from the right at a number a. Continuity from the right means the direct substitution works in this kind of way. When you take the right-hand limit, those kind of limits we looked into in section 2.1, you get the value f of a. So direct substitution works again on this end. And we will say something is continuous from the left at a number a if the left-hand limit instead works out. If we say a number is continuous, say, at a number a, like on, dang it, didn't want to zoom out too far, but here we are. We said this is continuous at x equals 2, but that automatically implies it's continuous both from the left and from the right. So it's a really strong statement. We'll never have to say it's continuous from both the left and the right. It's already conveyed when you said continuous at x equals 2. So now when you're saying continuous from the right, we're often meaning only continuous from the right when we make that statement. And same deal when we say continuous from the left. So the best way to really think about these definitions, just like on the initial definition, is to draw out a graph that conveys this information so we can make a connection in our mind's eye. What does the picture actually look like from single-sided continuity, continuous only from the left, and continuous, that's only from the left, sorry, and continuous only from the right? So we're going to draw a graph with multiple problems on this one. Once I get a steady hand. Okay, let me try again. Here's my horizontal axis. Kind of hard today for some reason. Here's the vertical axis. Now let's put a problem somewhere here, way out to -6, just to space things out. At -6, I'm going to put a hole in the graph right here at height 3, and a solid dot down here at height 1. Then let's go 1, 2, 3, 4, 5, 6, 7, 8. So let's include 2 more problems on this graph. At 5, I want to have the same kind of thing, a solid dot and an open dot. So let's put an open one at height 2. I guess we can make something negative. Let's put 1, 2, 3, 4, 5. Let's go here. -4. Let's put a solid dot at height -4, where the value 5 is. And for this 8, let's put in at height 4, just an open circle like this, but nothing else. So it's going to be undefined at 8 itself. Now for the rest, let's draw in the curve. The first thing I want to do is connect the open dots in the middle. So you can connect this in any way you'd like. I just put in a wavy line, make it look interesting. On this one, I just want the curve to come in to the left and land on the solid dot. And it could be any kind of curve whatsoever, just has to pass the vertical line test. Let's do a weird one this time. It could be a horizontal line. No one's going to stop you from drawing in a constant function on this domain all the way up to -6. So again, pretty weird function. Usually we put in some variation like linear or maybe polynomial looking, but that would qualify. It's a bona fide function. Optional arrowhead just says it's going to the left forever in this flat constant height. And then from here, let's let this shoot up in a nice linear way. Passes through the hole, continues on. And that's our whole function. It comes in 3 different pieces, but this is one function with multiple problems for sure. We'll call that function y equals f of x, or just f or f of x for short. It definitely has character. I agree with that, Haley. So here's our function altogether. Now we're going to look into single side limits on these 2 spots. But notice right here at 8, we can make a statement immediately on that one. Recall, let's just move this down as a screenshot. It's not fun to scroll up and down constantly. So from the remarks above, the very first bullet point said, if you have the function f as continuous at a number a, think a is 8 on this statement, it implies f at that value is defined in the first place. But we have a problem right here. We have that f at 8 is undefined. And this tells us just immediately and automatically f is not continuous at x equals 8. I'll put a box here as just not really an answer to a question. This is just us looking through the information. But this is one conclusion I'll put in a box that we're emphasizing through this remark. F at 8 is undefined. There's no solid dot anywhere, so there's no continuity there. But also think in terms of if this was continuous, you could draw it without ever lifting up the pen or pencil. When you drew this, you would have to lift up your pencil once here. That's one discontinuity. Then refine up to here. It jumps down, so that's the second discontinuity. Then refine up to here. This discontinuity also causes to lift the pen or pencil. So that's another way to think of, that's a discontinuity right there. So now let's look into the other ones. Oh, sorry, didn't want to scroll that far down. You have very limited space, so it's always kind of tricky to try to fit everything in without making it feel like we're cramming things. Let's now focus on -6. At -6, we can take 2 different kinds of limits. We can take the limit as x tends towards -6 from the left of the function. We can take the limit as x tends towards -6 from the right with the plus symbol of the function f of x. And we can also just compute f at 6 outright. Let's start with a thing that's more familiar. This is the function value. Oh, hang on. I want -6, not +6. Sorry about that, especially to anyone who's working in Penn today. I want -6 on all 3 of these to compare with the limit statement that we see here. So f at -6, well, that's at height 1. So we would say that this is just equal to 1 altogether. Now we have 2 single-sided limits to get through. If we come in from the left, that's this one with that negative sign, that means we're only coming in this direction, and the height, it's 1 no matter where you're at. The closer and closer you get to -6, well, you're always exactly 1, so that's the value of the limit on this one. Value here just turns into a 1 altogether. But what if you came in from the right? That's the one with the plus, the right-handed limit. That means you're on this part of the curve. Getting closer and closer to -6 means your height is increasing higher and higher. It approaches +3. So the function is going to +3. That means the limit is 3. But for continuity to exist, we need equality. And there's only 2 that are equal. the left-hand limit and the function value. So from those two, we can conclude, well, I was trying to put in a curly brace, there we go. Since the limit as x tends towards -6 coming in from the left of f of x is equal to f at -6, we can now say f is continuous. By the way, CONT and dot is a great shorthand for continuous. So if you run out of space like I am on this, that's an awesome shorthand. F is continuous at x equals -6. That statement's not fully correct until we say only from the left. So continuity from the left meant the single side limit coming in from the left was equal to the function value. And that's what we had here. Just those two parts matching, giving this result here. Doesn't match if we put in the plus sign, so it's not continuous from the right whatsoever. So that's a pretty weird kind of discontinuity. And here's a really great punchline to all of this. Continuous from the left meant we came in from the left-hand side and we ended on a solid dot. That's what continuous from the left always looks like on a graph. We're not continuous on the right because we're approaching an open dot. So you can spot these in that kind of way, just by considering where the solid dot is. If they were both open dots, it would neither be continuous from the left nor the right whatsoever. Well, that's one down. We'll take a look at the view from 5 here, but any questions so far? Okay, it's definitely pretty tricky. Continuity, the original statement is not too bad, but single-side limits, they're tricky on their own. And so single-side continuity, we expect them to be tricky as well. So let's see what's happening at 5. Like before, that's a pretty good review problem. We'll take two single-side limits and a function value, take the limit as x tends towards -6. Let's do this in the same order for the sake of parallelism. -6 coming in from the left, like we did on the left column of the function f of x. Take the limit as x tends towards -6 coming in from the right of the function f of x, and then also evaluate f at -6 as well. Okay, so we're now, oh, sorry about that. I should have really focused on what we're doing here. We're looking at 5, so this should have been values of 5. Must have not drank enough coffee today to get started. I want to do the limit around 5, so let me backtrack on that. Take the limit as we come in from the left, as we come in towards 5 from the right, and also evaluate f at 5. So just for the sake of the notes, that was my typo right here. Trying to look at 5, so I should have put 5 in all those spots. Okay, aside from that direction, we can now do these values. Starting with the function value, if you're at 5, you just go down, hit the solid dot. It's meant to be at height exactly -4. So that's our output on that one. Now let's take a look into the single side limits. Anyone have the value for, say, the left-handed limit? Yeah, absolutely. As we're coming in from the left, we're on this side of 5. Height gets closer and closer to a height of 2 altogether. So we can put a value of 2 on this one. And that's a mismatch. This tells us automatically it cannot be continuous from the left because it doesn't match the function value f at 5. But when we come in from the right, it's dropping down in an orderly, linear way, getting closer and closer to -4. That's where the function's heading towards, that value. So the right-hand limit is -4 as well. And we have a match this time. So this match here was because those two values lined up. But this time the match is from these two values. So let's make a conclusion on this one. Let me just clear off some space here, kind of painted myself into a corner. We can now say, based off this information, since the limit as x tends towards 5 from the right, so with the plus sign of f of x, is equal to f of 5, f is continuous. I'll use CONT for continuous at x equals 5 only from the right. And I almost got that to fit. But if you zoom out just one more factor of 10 degrees, only from the right. So that's what right-hand continuity looks like. We match up those values. If the limit comes in with the plus sign and it matches the function value, we have right-hand continuity. But let's put both of these ideas together. We were continuous from -6 from the left, because if you go from left to right, we landed on a solid dot. And we're continuous at 5 from the right, because when you come in from the right-hand side and move in, we landed on a solid dot there. You change the order of these dots, you change the direction of the continuity on both of them. And if there's an open dot, this one is just not continuous from the left nor the right whatsoever. Even if we put a solid dot somewhere else, it would still have that value or that problem. It's now defined, but still it wouldn't be continuous from neither the left nor the right. No continuity at all, even with the solid dot defined somewhere. I'll erase it so we can leave stand. F of 8 is undefined. That means no dot whatsoever. But in a nutshell, this is what single-sided continuity looks like for these kinds of problems. Well, any questions at all, folks, with these so far? Okay, comparing information with what we said back in the day, we would have said the limit as x tends toward -6. It doesn't exist at all. That's because the single-side limits are coming out as different. And that's a hint there might only be single-side continuity. And another interesting thing to talk about with these is this is a particular kind of discontinuity as well. On our first graph, we just had 1 point removed. But here, this is a humongous kind of discontinuity. The graph literally jumps up to another height and it continues on. It jumps down to a different height, continues on. This one's a removable discontinuity. But the other ones are different. We'll call a discontinuity like this, where a whole region of a graph moves away. It's kind of a nice definition. It's called a jump discontinuity. So there's a jump here, and this is another jump discontinuity. As well here. So that's a lot of definitions to start off the notes. Our goal is to really kind of solidify this in our mind with a couple practice problems before we see how to evaluate limits using properties of continuity, the end part of the notes. But really, this is a hard topic to really start off because they're pretty technical information, lots of stuff we're putting together all at once when we're looking at single-sided continuity. Well, any last questions, comments, or thoughts, folks, before we turn to the first examples? Okay, so here's what some of the problems could look like. This one's a really fast one, just to try to put into context what do discontinuities even look like in a real applied setting. So this one's probably pretty familiar to another applied problem we looked into, where we're looking into the amount of a drug in a patient after regular infusions. This one has a different context. It says, imagine you have a large pool, and every day you dissolve 28 ounces of chlorine into that pool. We're going to model the amount of chlorine by the function f of t. So horizontal axis is amount of time progressing. Vertical axis is y equals f of t, which is that amount of chlorine in the pool. It looks kind of like a concerning graph because if we look at the trend, it's moving upwards and it has a particular shape. On day 0, we have 28, let's see, what are the units on this? Ounces of chlorine in the swimming pool. As time goes on, that chlorine evaporates in some kind of way. And by day 1, we're at, say, maybe 7 was that ounces of chlorine. That's when you dissolve more. So the height of the curve jumps up. Now we're maybe 34 if we're estimating ounces of chlorine. And this repeats on a daily by daily basis, always putting in the chlorine apparently at the same exact time. This pool might become unbearable to be in after a while, so it's kind of a concerning graph as well. Haley says, so will all of them be continuous from the left, but not the right, excluding 7. Oh, that's a good eye on 7. I hadn't thought about that on this one. But yeah, that's what this one is all about. It's asking what type of discontinuities does this graph show? Well, if we look at these, if we draw a line moving into the solid dot, we came in from the right-hand side. So yes, absolutely. We have all of these values continuous from the right at these endpoints. So we can start by saying the graph is continuous from the right at, ordinarily we write x equals, but the context is for time. So we'll say time equals 0, 1, 2, 3, 4, 5, and 6, ending on that one because as you said, there's no continuity from neither the left or the right at 7. So here, this is just a full-on discontinuity. Neither continuous from the left or right. Well, that's kind of a big statement. So sometimes just the quickest way to say it is just discontinuous. If it had single-sided continuity, we would have mentioned that. So let's say here, i.e., in other words, it's discontinuous at t equals 7. Well, other thought on this one is, what is the type of discontinuity? We've looked at 2 kinds so far. The removable discontinuity just means there is one hole in the graph, but these are all jumps. They jump upwards to a value as time progresses. So we can further clarify by saying these are all jump discontinuities. And so that's pretty much the end of the question. Again, this is kind of a fast one to think about what continuity and a discontinuity would look like in context of an actual applied setting. But any other questions or comments getting through this one? Okay, well, let's try out the next exercise. This one is a graph with lots of different problems going on at once. But overall, this is just one big review problem of all topics continuity we've been hitting on so far. We have different kinds as well as we're going through. Part A is asking us to state the numbers where it's discontinuous. So that'll be the first thing we do. Then we'll also state the type of discontinuity that we see as well. But really finding a discontinuity, again, is not too bad conceptually when we're looking into a graph. If we read this going left to right, we'll hit spots where problems just occur one after another. Here's the first problematic point. There's a hole there. The function's totally undefined at that spot. So there's a discontinuity at x equals 1 immediately to start. Let's do the green part first, just the points where it's discontinuous. It's also discontinuous at 2 for the same reason. There's a hole in the graph. Whether there's a function value defined or not, these holes give us discontinuities. So here's one at x equals 1, x equals 2, and anyone happen to see where the next discontinuities will be? From the chat, Emily states 4. Absolutely. June says 4 and 5. Yeah, good call. These are the next two discontinuities. Notice no one said 3, and good call on that one. 3 is pretty weird, though. It's a really sharp corner on the graph. Not something you see very often when you plot functions, but it's something that can happen to functions. This one is continuous, but we'll come back to that when we're talking about differentiability. This has a weird feature on the graph. We'll later on say the function is not differentiable there. So if it looked weird to you, you're on the right track. But in the view of continuity, you can draw that without ever lifting up your pen and pencil. It is continuous at 3. So folks stated in the chat, the next discontinuity is at x equals 4. And the final discontinuity is right here at x equals 5. Next thing we want to do is categorize these types of discontinuities as we see. When we say the type of discontinuity, we're less about continuity from the left or the right, and more about writing these categories that we've been hinting at. At x equals 1, this is a removable discontinuity. And same problem when we come up here to x equals 2. Both of these are considered removable, so removable. I'll write just as a shorthand to save time writing down notes. DISC will stand for discontinuity. Or if you want to add just a little bit more detail, you can write DIS, CONT, also a great shorthand for discontinuity. That we pass through here, and anyone recall the type of discontinuity on this region? What would you say this one was called? Yeah, go ahead. Yeah, absolutely. So this one is a jump discontinuity. I'll use the shorthand, discont for discontinuity. And we have a new one. Well, we might have talked about this as a discontinuity when we were in, say, section 2.1, but it hasn't come up in a very big way yet. This one's a pretty interesting value right here, right? Limit does not exist at x equals 5, and nonetheless, we can still write down a limit statement that would read like this. I guess I can't do that. If we attempt to take the limit as x tends towards 5 of the function f of x, well, that one is moving up, up, and up without bound. Vertical line is just to emphasize we're looking into a vertical asymptote on this graph. The limit comes out as infinity, and this automatically implies, right, I would just say last equation implies that f is not continuous at x equals 5. As folks stated in the chat, that's a discontinuity. A vertical asymptote is a true barrier for functions, not horizontal ones. You can cross a horizontal asymptote depending on the function, but vertical asymptotes are special. The curve can never connect through and cross. You really have to lift up your pencil and start on the other side and draw it coming down. So that caused a true barrier. We haven't named this discontinuity type just yet, but if you're getting an infinity, I think a lot of people would say it's reasonable to call this one an infinite discontinuity. And that's the type that we're seeing there. If you ever get an output of infinity, we've lost continuity, and this is the description for it. So it's due to that, due to the vertical asymptote, Here's the new discontinuity we incurred, infinite discontinuity. Whether you get positive or negative infinity, the conclusion will be the same. Okay, so that's the rundown of various limits, discontinuities. But for part B, again, this is one big overall review topic. We're returning to the question of single-sided continuity. For every discontinuity we stated here on part A, determine if f is continuous from the right, from the left, or potentially neither. Let me zoom out just a touch. Okay, let's try these in turn. X equals 1. What would you all say for x is 1? Does this look like continuous from left, right, or neither for the third possibility? While we're thinking about that, let me open something real quick. Sorry for the fast visual distraction there. Definitely kind of tough to visualize in a certain sense, right? Yeah, good call, Haley. This one is a true neither right at 1. But this is a tough topic again, so let's return to this graph just as a reminder and put it into context as we're thinking about that question. Once I get the red dot out of the screenshot. Okay, back down to the problem. So this one, just as you said, is a true neither, right here, is a true neither, and same for 2, it turns out. Continuity from the left and the right is actually pretty restrictive, it turns out. Actually, this is kind of hard to fit in, but let me zoom to about here. This was continuous coming in from the left, we said in the notes, because when we came in from the left, we landed on a solid dot. It has to really look like that. Continuity from the left or the right is conflated with jump discontinuity. They actually go together. So here, there's no jump discontinuity. We're not landing on any solid dot. There's no solid dot whatsoever. And likewise, continuous from the right means we're coming in from the right-hand side only, but landing on a solid dot. That solid dot is the major feature for single-sided continuity. And even on 2, when we come in from the left or from the right, we're never getting closer and closer to a solid dot. It's down there. The curve has to go into the solid dot for single-sided continuity. So we can say for both x equals 1, x equals 2, neither. Both of the same kind. And notice they were both jump discontinuities when single-sided continuity happened. And that's a required feature for single-sided continuity. Let's put that here in the notes just to tie this together. Continuous from the right or from the left, both of these requires jump discontinuities. But that's kind of nice in a way, because if you've categorized your types of discontinuities, you'd realize there's actually just one candidate. X equals 4 was the jump discontinuity. So let me add just one more. This one was an infinite discontinuity, so we can say x equals 5. Neither as well. The curve doesn't stop on a solid dot, it just keeps on going up and up, higher and higher. But this one is a jump discontinuity, so there is single-sided continuity on that one. We just have to say which type is it? Is it continuous from the right? Or is it continuous from the left at 4? Anyone see which kind of continuity this one is? It would be a jump discontinuity, but would it be continuous from the left or continuous from the right on this one? Turns out it wouldn't be from the right on this one right here, it turns out. Again, it's really pretty tricky. This one's coming in towards the left, landing on that solid dot here. but only from the left do we hit that solid dot. So that means this one's continuous from the left-hand side. So it's right here, continuous, only from the left. Or you could just say continuous from the left for a shorthand version. Yeah, exactly. And because single-side continuity is such a tricky thing, let's really check this. If it's continuous only from the left, a certain kind of limit has to work out. We have to take the limit as x tends towards 4, but coming in from the left means a left-hand limit of the function f of x. As we come into 4 strictly from the left-hand side, we're getting closer and closer to a height of 2. And at the same time, f at 4 is also equal to 2. So continuous from the left means the left-hand limit and the function value both match for an output of 2 altogether. On paper, it just means as we take the left-hand limit, we landed on the solid dot right there. Well, that's the rundown of continuity classifications, part A, and another look into single-side continuity, kind of the challenge topic for these notes, in part B. Any questions or comments so far, folks? Getting through either one of those? Okay, these, in my opinion, are challenging the first time you see this information. If today, here in class, was the first time you saw this, it is not easy to absorb all this at once. So one thing you could always do to really help with this kind of lecture notes is anything you do to kind of skim the section 2.3 in the textbook is a big help. It'll help your mind to kind of absorb these topics when you see it again in the notes. But also when you go to do these problems again in WebAssign, it'll start to click. You can come back here, see how we did them in class, and you'll be looking into similar kinds of content as well in the WebAssign homework set. But for now, let's say with our remainder time, this is the final topic, evaluating some more limits down below. They look like pretty nasty limits, especially with what we've done before, but this is where continuity really starts to shine. Recall, continuity is a property of direct substitution at its heart. That's what it's all about. And a lot of the functions we've been dealing with in an algebra situation, in algebra, on our algebra background, they turn out to be continuous functions. But theorem 4 starts off by saying, if I give you any two functions that are continuous, and any real number c is a constant, so it could be, say, 5, 12, 0 even, then all these recombinations of functions down below are also continuous. Add a continuous function to a continuous function, that's still continuous. Same if you're subtracting. Constant multiple is continuous, and even multiplying and dividing functions are continuous, provided that you're not dividing by a value that comes out as 0. So this is just the quick way to get continuous functions from other two continuous functions. But theorem 6 is even more powerful. This is essentially a catalog of all the kind of functions you might have been exposed to. Keep in mind, our course does not have trigonometry as a prerequisite, so we're not going to emphasize that anywhere in our lecture notes. If you're reading a problem in the textbook and a trigonometric function, sine, cosine, and so on show up, you're okay to skip that example. That's content we can't bring directly to this class. Let's go through these just to look into the catalog of what's continuous. Let's start off with polynomials, power, and root functions. It's a great category of functions, all continuous. So they could be, for example, a function f of x equals x squared plus 3x. So that's a degree 2 polynomial function. If we want to call it a power function, that just means we have another function, g of x equals, say, x power 7. And that's your only term. It's just a bona fide polynomial as well. Another function called the root function could be something like h of x equals cube root of maybe x squared plus 3. So I have a composition of a polynomial and a cube root function, this one would also be continuous as well at the same time. And if we look into our limit laws from back in the day in section 2.2, that's essentially what these things were saying. Take a look into limit law 10, for example. If I zoom into it, it'll be easier to read. It's saying you're taking a root function, the nth root of x, as x tends towards a, and you just plug in the value, get a result. Or maybe you're looking to the power function. That's limit law number 9. The limit as x tends towards a of x power 9, maybe it's x power 7, you just plug in the number and raise it to that power. When we use that, we're just doing continuity at the same time. So there's lots of properties of continuity inside of these notes, which is kind of nice. And it expands even further. An exponential function could look like this. Say f of x equals 2 to the power of x. Or maybe g of x equals a base e exponential to power of x, where e is just the Euler's number, approximately 2.72, just a weird base that'll come up quite a bit in this course. Because we're saying that these are continuous, it means if we ever do a limit involving an exponential function, it's going to be like the world's fastest limit. You would go limit x tends towards, just for a random example, let's say 3 of, let's go with 2 power of x, why not? Because this is a continuous function, direct substitution is in effect. We just throw in a 3 there. It's 2 power 3, and so we get an 8. That limit is totally done. Rational functions, however, these ones are finicky. This is where we had to work a little bit harder when we were in the section notes. Actually run out of colors. Let's go with gray on that. Rational functions can cause a little bit of extra work on our part. But what we mean by a rational function is anything along these lines. F of x equals, put a polynomial, any polynomial whatsoever in the numerator, put another polynomial, it doesn't matter what degree you pick, put another polynomial in the denominator, and that would be another rational function. But this is a nice rational function. It's going to be continuous on its domain. The domain of exponentials is all real numbers. The domains of all 3 of these functions, whether it's a polynomial, power, or root function, also all real numbers. But sometimes the domain excludes a point whenever you might divide by 0. That's impossible in this function. The smallest number you ever get for the denominator is 1. The domain is all real numbers, so if the limit comes up for this one, say you're taking limit as x tends towards 0 of x squared plus 3x minus 3 over x power 6 plus 1, our first observation is that's a rational function. The domain is all real numbers, so 0 is included. If you plug 0 everywhere inside of this, you would get negative 3 over 1 for a value of negative 3. And that's your limit. We don't have to do anything further with that one. So why did we have to work so hard in section 2.2 as opposed to what we just did? It's because we were picking values not in the domain. That's where all the drama was in this section. Let's see if we can find one to end the course with. This one will do the job. Part A on example 4, that's just another rational function. But we were heading towards negative 3, and that's not in the domain whatsoever. That's what caused the whole problem. Plug negative 3 inside there, you divide by 0. So we had to do some work algebraically. We factored, we exchanged to this function, but hey, that's another rational function, right? It's a simplified form. It matches the original, except at negative 3, but that doesn't affect the limit. And so right when we got to here, negative 3 is in domain, so we plugged it in. There it is plugged in, and the limit's done. Essentially the same thing we're doing here, except this one had domain, all real numbers. So that's what we're going to look into to end the topic on continuity. It's a hard topic to start, but once we loop back to what we've been doing all along, taking limits, I think you'll like these problems because these functions are all continuous. So it's just going to be direct substitution on every single one of them. If you saw a random problem on an exam and it doesn't work with direct substitution, just do something algebraically to simplify it till you get a continuous function and then use direct substitution again. So that's the punchline for limits so far. Well, any last questions or comments, folks, before we end class today here on the notes? Okay, and one thing I forgot here is I think I accidentally skipped over this example. I don't want to leave this one off. So just to make sure I really hit this one, let me put it here. And this is going to be a visual reminder for me. I'm going to undo this when we come back because I said this is a problem that could be asked, say, on exams like exam one or the final exam. So we'll make sure that we do this example number 3 when we come back on Thursday. But have a great night, folks. If you have any questions, I'll be happy to help out. So otherwise, we'll get back to it on Thursday. Like I mentioned, I'm going to call the Pocatello Testing Center. I might have sent that information wrong. Make sure they accept exam scheduling on Monday, February 2nd, for anyone who might want to schedule a little bit earlier. But have a great night. I'll see you all later. You bet. Thanks. Have a good one. Yep. Take care.